and then we will go on to talk about correlations. That's what the title is. So here, we need to have that C is strictly positive, the real number that is strictly positive. U is a positive function of X. The finite expectation is for U, not for X. Because that's what you're using to. Finite expectation is for U of X, not for X. And then here, when you write the expected value, it's U of X here, not inside it. U of X times F of X. And then you split into two events. The event X larger than or equal to C, and the event X greatly less than C. And then you drop this. Why can you drop this? Because F of X times U of X is positive. That's why you have the condition that U of X is a positive function of X. So now you cannot extend from this. If you don't have that condition, the theorem doesn't work. Because this is the only reason why you can draw that. You have the integral of a positive function here. So it is larger than 0, so you can drop it and have something that is larger than the rest. Now on this set, because X is larger than X here. Let's have one mistake coming here. Tell me what the mistake is. U of X, right? So because on this set, U of X is larger than C, you can replace U of X by C and still have something that is smaller than what was there before. Now, when you do this, okay, U of X larger than or equal to C, and that's probability that U of X is larger than C, because the integral of the density over a set is equal to the probability of that set. That's why this works here. And therefore, you can solve from here backwards. You get the probability that U of X is larger than C is less than or equal to the expected value divided by C. You can only divide by C and have that inequality if you're starting by C positive. Otherwise, when you divide, you have to flip the inequality. Right? So it is important to have that condition. Otherwise, it doesn't work too. You just take any C and put it here. This is not true. If I put here C equal negative 1, it cannot work. So, and question 2 technically was supposed to just be included into question 1, because question 2 is an example of application of question 1. You said the function x, the random variable x is strictly positive. The expected value is 3. And so we want to show this, that the probability that x is larger than 6 is less than 0.5. So to apply the Markov inequality, what we need is to define the function u of x that is a positive function of x that has a finite expectation. And then we can apply that. So u of x here in this case is equal to x. Because x is positive, by definition of the problem, this function is a positive function on 0 plus infinity. Therefore, which is the support of x, because x is larger than 0. The expected value of x is given as 3, so it's finite. Therefore, by the Markov inequality, probability that u of x is larger than 6 is less than expected value of u of x over 6. U of x is x. And that's why you get 3 over 6, which is 0.5. In general, if you see a question like that and you don't have any distribution given to you, you need to know that it's an inequality that you need to use, either Markov, Chebyshev, or the incentive inequality. That's one of the three. If you have a question that is asking you to put the probability of an event less than enough, you know it's one of the three things. And question 3, you have f of x, y equals cx over y. So I think this is the last problem we actually solved in class here. All I did was to switch the x and y here. Side. So find C such that this function is a distribution, which means first sketch the region. That's the advice I gave. Sketch the region. The line y equals x because of x less than 1. And then you put the boundary of y that is given 1, 3, 1. And I said x is positive, so x stops here. So know that this is the range of y. And then you have the region of interest. So this is the region where the density is not equal to 0, and everywhere else it is 0.
Dr. Longla?
Yes.
I have a question about that graph. How did we know that the boundary line was y equals x?
Because here you have x is less than 1. You have to define the region where x is less than y. To do so, you need to draw the line x equal y first. And what we did is draw that line, and then you select a point either on this side or on that side. Check the inequality for that point. If it works, then it is that side.
I understand why it's shaded up there. So I guess where that's shaded, I guess that makes sense because x is always less than y in that shaded region. I guess I was just thinking of a different boundary line, but I think that makes sense what you said.
Okay. So you always look at the relationship at the boundary between x and y. This is the only relationship that was given there. It could be anything. This could be x less than y squared. It could be x less than y cubed or x cubed less than x. So that's what you're going to use to draw the boundary. And then I said that here. In class here, I said that x is assumed positive because you can have a negative density. If we let x go to negative here, you have a negative number as a density, which is not possible. Density is always a positive function. So that's the reason why whenever it's defined like that, intuitively, that is can never go below 0. And so at that point, I just say, okay, make sure you are assuming that x is actually larger than 0. So put it there, write it down, and I said, assume that it's larger than 0. Because otherwise, you won't have a density. If x is not larger than 0, you don't have a density. There's no question to that. The most difficult thing is to use that graph to answer the question. How? You know the integral over this set needs to be equal to 1. Okay, you know the integral over this set of the density needs to be equal to 1. How do you integrate? Just pretend that you put a negative infinity to infinity, negative infinity to infinity as usual, equal 1. And now you look at the region where you are. If you fix y here and you want to go through x, what are the boundaries of x? X starts there and it goes all the way to this. So it's a 0 to whatever is here in terms of y, and that is y. So it's integral from 0 to y. And then the range of y is 1, 2, 3. So integral from 1 to 3.
Dr. Longlet, how did we get the equal 1? Where did that come from?
That's the condition that is given in the lecture. The integral of a density is equal to 1.
Okay.
And the sum of probabilities is equal to 1. That's the main condition that you have in the definition of a probability distribution or a probability mass function. The probability of the whole space is 1. That's the sure event, the thing that will always happen. You are sure to get something. So the chance for that is 100%. If I say, come into this class, get a student, you will get a student. The chance of getting a student is 1. You start having issues when I give you the specifics of that student. Then you start thinking, will I find a student inside there with these specifics? That's where the thing changes. And now this integration gives you 2c, and then you set that equal to 1. So you get c equal 1/2. And that's, you can see, it's the only value of c that you found. So only one c can make this a distribution. Meaning if I put any other number here, what I get is not a distribution. Are we good? Now next, B, find the distribution of y. What I said about this is when you have that distribution and you want to find distribution of y, you integrate with respect to x. When you want the distribution of x, you integrate with respect to y over the range that is given. That's how you do it. So here, if you want the distribution of y, you have to integrate the density that is given with respect to x. But how do you integrate with respect to x? Again, that's where the graph comes in. If you don't have the graphs, you can't have the answer. How do I integrate with respect to x? It means y is fixed again, and I'm integrating with respect to x. X goes from that bottom, 0, all the way to the thing that is related to y here. What is it? X equal y. So that's why the integral is from 0 to y, because those are the boundaries when you are integrating with respect to x. And so you compute that integral and you figure that you got y over 4. But again, that formula is true only if the y that you fixed is between 1 and 3. Otherwise, you got 0. That's why when you're reporting, you need to remember that it's 0 elsewhere. Because if you write down that this is everywhere, you don't have a distribution because the integral will not be 1. Now you can check that if you integrate this thing from 1 to 3, you get 1. That's right. Why we continue. Now, let's see, find the distribution of x given that y is equal to a. This is one of the things that I was starting asking you guys. What's the formula? What's the formula of the for a conditional distribution? We can spend like 10 minutes to figure that out. So the formula is the joint distribution divided by the marginal distribution of y. That's the definition. If you want to find the conditional distribution of x given y, you take the joint distribution and you divide by the distribution of y, which is the same sense with so have the joint distribution, and I said when y equals a, so all you have to do is replace y by a, replace y by a here, replace y by a here. And so you divide everything, and then you get this. And again, you need to remember that that is only true when A and X are in the range that is defined by the joint distribution. So A has to be between 1 and 3, and X has to be between 0 and 8. Otherwise, it has to be 0. Of course, for those who did that, I didn't take too much into account the fact that somebody forgot to put 0 otherwise. Now here, question D. It was the question to see if you remember what is the range of the variable actually. Because it's not because a number is written here that you're just going to put that in the integral and start computing. So X, when you look at the graph, and let's go back to that graph again. It's always about the graph. What is the range of X? 0 to X is 0 to, is that one? Yeah. The range of X is from 0, which is here, all the way to 3. That's where it is. And so, bottom line, you're not supposed to have a value of X that is out of range. The range of X is from 0 to 3. -1 is not from 0 to 3. So this probability has to start where the range of X starts. So first of all, you're going to get rid of everything that is not necessary. So it's equal to probability from 0 to 1.5, because before 0, everything is 0. There's no X there. And now it's after this that you start thinking integral. When you're thinking integral, you need to be careful. How do you integrate? And that's the graph that I put here for it. You want X to be from 0 to 1.5. So you have to bring that here. Sketch this line from 1.5 up. See where you cross the region, and that's the region of interest. This is what you want to find the probability of, this whole thing. Right here. You have two options. Find the probability of the complement and take 1 minus it. That's a lot easier, but I didn't do that. I did the most difficult one. Set up this integral and compute. To set up this integral, you need to split. You need to split part of Calc 4, which is why it's not something that you must do. You need to split the integral. Why? Because the boundary changes here from this to that, and then from here goes in. So you need to split and have 2 regions and 2 different integrals. Over this region, you have a rectangle. Easy to set up the integral over a rectangle. That is this. That's the rectangle you have there. X from 0 to 1.5 and y from 1.5 to 3. So that's this part, easy. Now when you remove that rectangle, you still have this piece here to take the integral over. And you cannot compute it the way you did this one. So you need to see that first you fix y here. And you integrate from 0 to this value. You integrate from 0 to the value that is here. And that value is y. Then you integrate y from 1 to 1.5. Okay. This is the part where I say things have been removed in this first. I don't want to do this with you. I'm explaining, I'm using this test to explain this, but there was another way to do it. I'm using this test to explain this for those of you who need it. This is how you compute probabilities in 2 dimensions. The set is not always direct and it can have any form, and you need to use the knowledge from Calc 4 to split the range to have the proper integrals. Otherwise, you will almost certainly always have wrong numbers as answer, either negative integrals or integrals larger than 1 as a probability. So this is why I provided this answer the way it is. Now, if you want to do what is within the range of the assumptions of this class that you're not forced to know Calc 4, then you can say that that probability that 0 is less than x less than 1.5 is 1 minus probability that 1.5 is less than x less than 3. This we know because this is the complement of that set. Now computing this probability is just like the first case that we had. So 1 minus the integral from 1.5 to 3 in x. And the rest of the y, see where they are? It's a triangle. So the integral over a triangle is just like the integral over a rectangle. Just like you first fix the value of x between 1.5 and 3, so that's integral in x from 1.5 to 3. With respect to y, when I fix x, y goes from this, which is, what's the value of y here? The line is y equals x, so this is, if this is x, what's the value of y?
Is it X?
So y goes from x all the way up to what's the value of y here? 3. And you put that density inside x over 2y. And you compute this, you get the same answer. And it's not changed here. Okay. And you don't have to do the splitting and all the things that I done here. Any questions about this? All right, so this one, and then we had question number 4, which was an application of what we had as Bayes' rule, law of total probability. We had 2 problems like this. One was with a company that has 3 factors, and each of them was produced at a certain rate, some defective items. Remember that? That's exactly this.
Dr. Longley, can you straighten the page so that we can see the bottom corner?
So that's exactly what is going on here. And then we had another example with balls, but a lot more balls, and we just wrote these and choose this, and that's the answer. Bottom line, we have 3 options when we are selecting balls from the first arm to put in the second. So you take 2 to put in that second. You don't know which 2 are going. That's where you have options. Maybe 2 blue went to 2, maybe 1 blue and 1 red, maybe 2 red went there. So you have, that's why the sample space splits into a union of 3 disjoint spaces. And that's what I call red, blue, or blue. And now you need to compute the probability of having a blue in each of those cases and add them because they are disjoint. How do you compute in each of the cases? condition, then probability of getting that case. Condition, get the probability of getting the case. Condition, then probability of getting the case. So probability of getting a blue ball, given that I selected 2 red balls from the first hand to put in the second, times the probability of selecting 2 red balls, plus probability of getting that blue ball, knowing that I selected 1 blue and 1 red, multiplied by the probability of selecting 1 blue. Then probability of getting 1 blue, knowing that I selected 2 blue from the first hand to put in the second, times the probability of selecting 2 blue. So now you compute each of those probabilities. Here, in the first case, if I got 2 reds there, there's no chance I'm getting a blue out of it. That's why it's 0. I don't even need to put those numbers to multiply. If I have two blue balls, 2 red balls in, I can't select the blue one from 2 red. So the probability is 0. If I have 1 blue and 1 red, what is the probability of selecting a blue ball? There are 2 balls. One is blue. What's the probability of selecting a blue? 1/2, right? So that's this 1/2. Or that. Sorry, for this. For knowing I have a blue and a red, what's the chance of having a blue? It's 1/2. Now, what is the probability of getting blue and red in the first place? Which means select 1 red and 1 blue from the first hand to put in the second. So that's what we got 1 out of 3, 1 out of 2, and then select 2 out of 5 for the fact that you were selecting 2. Plus, now the third case, if I have 2 blue balls and I'm selecting 1 ball from that hand, what's my chance of getting a blue ball? It's 1 because there is nothing but blue here. That's why this probability is 1. And now the probability of getting 2 blues, what is it? Get into that first hand, pick the 2 blue balls that were there, pick 2 out of 2, then divide by the number of chances of selecting 2 balls out of 5. That gives you 1/2 times 6/10 plus 1/10, which is 2/5. Questions?
Dr. Longlaw, so when I first did this problem, I had that selecting a blue and then a red ball was different than selecting red then blue. And I got an answer I knew couldn't be correct. So I ended up changing it to this, but can you explain why this is the case?
You know that when you're putting an order in the things, everything changes and you're not supposed to be using combinations anymore. You're supposed to be using arrangements because you're taking into account the order.
Yes, sir.
Okay. But if you do that though, and you respect what I'm saying, like don't use combinations, order everything, you will end up with the same answer. This is one strange thing about this kind of problem. So if you switch and you want to give a certain order to the things and you respect that in all your computations, you end up with the same answer. Why is that? Because red, blue, and blue, red, what is it? If I'm taking them at the same time, what's my chance of having 2 reds, 1 blue, and 1 red? I think 1 blue. Remove it from there. How many blues remain there? There are 2 blue balls in the first hand. I pick out 1. How many? 1. I pick that second one. How many chances do I have to pick that second one? Only 1. Right? And so, and if you are doing that and you don't take into account that fact that you are removing it and therefore it's only 1 that is left, then you end up with a different answer. Does that make sense?
Yes, sir. Thank you.
Okay. Any other questions on this? I think this is very important actually because of all the things that we do, this is one of the things that goes straight into statistics that we'll be doing. So, yeah. conditioning in, and what is the chance of having that case that you're conditioning? Goes into case studies, goes into many things that people investigate. All right, so next was and so the last one was, the last question on that was find the probability. Okay, let me make this comment here. Okay. There is always an issue with properly labeling the question. If you don't label the question correctly, there's a high chance of having the wrong answer. I actually give people credit for writing this correct, not finding the answer, because it's important to know that that's actually what you're looking for. If you don't know this, high chance that you're going to find the wrong answer. How was the question formulated? It says, it is known that the ball is blue. What is it? It's known that the ball is blue. It's condition. Conditioning on the ball blue. What is the chance that exactly one blue ball was transferred from the first one to the second? So what's the chance that blue and red were removed from there, knowing that your result is blue? Because they gave you the result. And if you don't do that properly, you would think that it's probability of blue and red and blue, and therefore you mess up everything. How would the question be formulated? What do you think? How would the question be formulated if we needed from you probability blue, red, and blue? How would you formulate this? Blue, red, and blue. Now that's for those people who know English, please. Tell us. I don't know that. Guys, formulate the question for me. The question that in this case would mean probability of selecting this is, I think we should start having points. It's long on that. So this is blue and red is from the first time. Select blue and red from the first time, and from the second, you select the blue. After doing this, I don't want to compute the probability, but to know how you would formulate the question so that there is no confusion. The question I formulated was, what is the chance that this? Now, how would we formulate this question, which is what some people computed, this one. How would the question be formulated for that? If tomorrow I give you the same question and I formulate it somewhere else, how would you know that it is this instead of this? No, it's just in English, just as an English statement that would mean compute this probability. Yes, sir. You feel in what you're saying that you use the word given, right? If you already use the word given, you know it is a condition. So probability don't do that, but I think that's exactly what she said. The probability of getting one blue and one red from the first time, then selecting a blue ball from the second. There is no condition here. So you do one thing, then you do the other one. You don't have the condition. But if you are going by knowing or given that you selected a blue ball and a red ball, what is the probability to get it? You see in the formulation that actually probability comes even after you have said given, right? After the outcome. In your statement, the word probability comes after that. Am I making sense? Because we say, given that the outcome is this, find the probability. That given is not before the word probability. And in the other case, it says, find the probability of, and then selecting a blue and a red, then the whole thing is after probability. Am I making sense? Yeah, that's silence. That's it. Am I making sense in what I just said? So that's what I think you should remember, those to separate the conditional probability from the probability, the joint probability of A and B. In one case, one event is before the word probability. In the other case, all of them are after the word probability. Now, so when you do that here, this is the base rule that we have. So we apply the base rule to answer this question. Because you're finding the probability of a condition given the outcome. So in this case, that was blue given blue red, as blue red over probability of blue, which in the original formula is written as this long formula that we wrote here. In the formula of the base rule, this is what is written. And that thing is P of B. Because we already computed it, we don't need to do that here. So it's actually just one question. I just split it into two steps for you to find this before putting into the formula. Make sure that I have the reason. All right, now let's look at question number 5. Here we have the discrete random variable and the TMF. And finding C as we have 6 values of X and Y. 1, 2, 3, 4, 5, 6. And I said just like the sum of everything is supposed to be equal to 1. So the probability of 1, 1 is C, probability of 1, 2 is 2C, probability of 1, 3 is 3C, 2, 1 is C over 2, 2, 2 is 2C over 2, and then 2, 3 is 3C over 2. The sum must be equal to 1. And so you add all of that, you find out that the probability that C, the only value of C that satisfies this is C equals 1 now. And then to find the marginals, you use the table as we did. Roll the table, put in the table the values of the probabilities that are given by the formula, given the C that you got. Add everything put there, add everything put there, and right here, you get the marginal distribution of X. And right here, you get the marginal distribution of Y, and you can copy like this. Then this expected value is just tripling the values. What is the expected value? The expected value, the moment generating function for XY uses 2 variables, not 1. One goes with X, the other one goes with Y, and that is plus. So it's expected value of e to the t1x plus t2y. You don't want to use t1 and t2, make sure you use two different symbols. And so what is that? It's the sum of probabilities times whatever is there. So you know the probability of each of the pairs. That's what was given here. That's what is in the table. So all I'm doing here is go to each of the pairs in the table, take the number that is here. That's the probability. And then plug in x and y into the formula t1x plus t2y. So that is 1 9 e to the t1 plus t2, 1 plus 1, 1, 18. And then replace x by 2, replace y by 1, plus 2 9s, then replace x by 1 and y by 2. Then 1 9, replace x by 2, y by 2. Then 3 18s. Then replace x, sorry, 3 9s, then replace x by 1 and y by 3. And then the last one, 3 18. Replace x by 2, replace y by 3. So that's it. You have that. That's the moment where you don't have to continue adding the element that is needed. It's for you to know that you understand that that's what is going on with that formula. That's what you need to do. Now, how to find the moment generating function of x? You plug in t equals 0 and t1 equals t. You get that formula. And what I was doing here was show you that actually it's same as, look, take 2/3 multiplied by e to the xt, x is 1, plus 1/3 times e to the x times c, x is 2, that's it. So you do it this way, you get the same answer as if you take this, you plug in t equal, t2 equal 0. You must get the same answer to show you that the joint MGF actually gets the marginal MGF without any problem. And it's the same answer. Whether you use a direct definition or you use the joint distribution. And the same thing for y works. You would say that's 1/6. And then replace y by 1, e to the t, 1/3, e to the 2t, 1/2, e to the 2t. Questions? And then by definition, the expected value of definition of the moment generating function, the expected value of xy squared is the derivative, 3 times the derivative, twice with respect to t2, 1 time with respect to t1 gives you x, 2 times with respect to t2 it gives you y squared, then plug in 0, 0, and you get the answer. Questions? And taking those derivatives here is easy because what? It's exponential. All you do is take down the coefficients. So take down the coefficients of t2 twice. 1, 1, that's 1 squared. Take down the coefficient 1, so that's 1.
Dr. Longla, I can't see what you're looking at. That's better.
Taking the derivative here with respect to t2 twice and with respect to t1 1 time for each of these. That's what I did here. Twice the derivative, that's the coefficient of t2 that comes down twice. Here it's 1. This is 1, so that's 1 9. That's why here you go 1 9. Then for the second one, you take down the coefficient of t1 1 time, that's 2. T2 it's 1, so 1 twice it's 1. 2 times 1 is 2. That's why you got 2 18. 2 and the 1 18. And here, take it down twice. That is 2 times 2 4 times 1 4. 4 times 2 8. That's why you got 8 9s. Then here, Take it twice down, you get 4. Take this down one time, you get 2. 2 times 4, 8. That's why you got 8 nines again. And then you get to this one. Take down 3 twice, that is 3 times 3. 9. Take down 1. 9 times 1, 9. Times the 3 that is here. So you get 27 nines. That's why you get that. Then you look at the last one. Take down 3 twice, that's 9. Take down 2, so it's 18. So you get 3 times 18 over 9. And then you just add it. Questions?
I still can't see
What's that? Now here, this is one of the questions that I asked you to do on your own after solving one. And I really like a lot of answers that I got from there. Many students have many different answers, not exactly what I have here, but those were also brilliant answers. I never thought. I really like how really those beautiful answers. What I did was just use that same formula twice. So A complement and B complement is probability of A complement minus so A complement and B, because the union of these two sets is A complement and the intersection of the two is empty. So those two sets are disjoint. Therefore, the sum of their probabilities is the probability of their union. So I have this. Then the one that is here, I go through B to split it. So B is A complement and B union A and B. And again, these two sets are disjoint. So the probability of the intersection is 0. Therefore, the probability of B is the sum of these probabilities. So this one is going to be probability of B minus the probability of this one. That is this. And now all I have to do is use the fact that A and B are independent. And again, this is one of the things that I want to emphasize. Remember to talk about the assumptions when solving the problem. Because it's only true because those assumptions are here. Once you remove the assumptions, the rest is wrong. If I remove here the fact that A and B are independent, then I don't have that this probability is equal to them. I need to justify it. Now after that, you can see here, we have a P of B that is a common factor. The P of B, the common factor is the 1 minus P of A. And then P of 1 minus P of A is P of A complement. And so you can put P of A complement as common factor of 1 minus P of B. And 1 minus P of B again is P of B complement. So the probability of the intersection is the product of probability, therefore they're independent. The other answers that I got from your classmates were a lot simpler. It was interesting. Any questions? The last thing was use Jensen's inequality to show that the expected value of x squared is less than the expected value of the square of x. So you need to give me that phi of x equal x squared, calculated secondary, show it's positive, so the function is value of x, that's the word. And moreover, the expected value of x squared is fine. By Jensen's inequality, phi of the expected value of x is less than the expected value of phi of x. So that's what this requires. Any general comments on this test? Now, what I can say about the proof of the first question of the Markov inequality, I use a continuous distribution, assume that I proved it. Some of you just proved it assuming a discrete distribution, right? which is fine. I accepted any of the two proofs. Comment that I do have is, in general, for those of you who would need these kind of things to go forward, you need to know when you prove something for the integrals, it's enough. But when you prove it for the sum, it's not enough. Why is that? Because the integral is first of all the sum. The integral can turn into a sum, and not all sums turn into integral. Right? The integral, for example, I can integrate a discrete function. It's just assuming that it's not the Riemann integral I'm talking about, it's the Lebesgue integral. In that case, my proof is actually including also the discrete case, because that integral will just be the sum over the sets that have non-zero measure, which is that sum that you have. Right? Does that make sense? All right, so today I wanted us, after the test, to talk about correlations, which is the topic that will bring us straight to our new life, which I'm hoping that you guys would like. So, first of all, given that's one. Oh. Of xy equals expected of x minus the x times y minus the of y. This is what we call the covariance of two random variables x and y, and this is same as the covariance of y and x. So this is symmetric function. It doesn't matter which of them you name first. It's going to give you the same answer. And easily, we can call that theorem. You can show that the covariance of xy is actually equal to the expected value of xy minus expected value of x times the expected value of y. So you don't need to always scale and subtract the mean before you compute the expected value. You can just compute the expected value and then you subtract the product of the two means. THEO theorem. That this thing is same as that. If I want to use the notation that I here, it will say that's mu xy minus mu x times correlation. Let's define as rho equals covariance y divided by sigma x. Sigma y, where sigma x is the square root of the radius of x. Sigma y is square root of the radius of y. And one thing that is sure is that like the components x, y, or the vector, absolute value of absolute value of the row is less than or equal to 1. When the row is equal to 0, we say that x and y are uncorrelated. The row equals 1, that is perfect positive correlation. And the row equals -1, that's perfect negative correlation. And I used to joke with this one, so as row equals 0 is when you don't know each other. You just don't care what people are doing. Row equal 1 is when you're organizing your wedding, you and your spouse have almost a perfect positive correlation score. And row equal 9 is -1 is when you're going for the divorce. Everybody's looking in some direction. Or you make it different correlation. Now, this example is an example that gets people confused because anytime people hear that, they start thinking that when the correlation is 0, it means that things are independent. No. When things are independent, the correlation is 0. The correlation 0 doesn't mean that things are independent. It just means that we are uncorrelated. If we are independent, if what I do doesn't impact you, then our correlation is yes. If everything I do impacts you, then there is some correlation between the two things. If anytime I go positive, you go positive. Anytime I go negative, you go negative. There is a strong correlation. So here, x and y are independent. And right here, I'm introducing this topic independent, which means f x of x times f y of y. This is the marginal distribution of x. That's the marginal distribution of y equals joint distribution of x, y. So the joint distribution is equal to the marginal distribution, or for discrete random variables, p of x, y equals p of x times p of y. So this is for the PMF, right? For discrete random variable. This is for the PDF for continuous random variable. Two continuous random variables are independent if their joint distribution is equal to the product of their marginal distribution. Two discrete distributions are independent. Two discrete random variables are independent if the joint probability of any two events is equal to the product of their margin. This is for all x, y, not just one pair of x and y. So if those two formulas, if one of these two formulas holds for all x and y, then we say that the two random variables are independent. This is also equivalent. This is also equivalent to probability that x in A and y is in B at the same time is equal to probability that x is in A times probability that y is in A for all A. So given any, for all A and B, given any sets A and B, the probability of being in A for one and being in B for the other is the product of the marginal probabilities. Then you say that the two random variables are what's that? B. I'm getting too slow. Are we good? So this is what independence is about. And this is what people like in statistics. Consider an IID sequence of all IID independent, identically distributed. So people are happy, everything just product, sums. And we forget about all the drawing the region and all those things. So for this example, what happens? That's the question. The reason why I gave the example was not for the joke, it was for the correlation. So what is, sorry, I didn't. So what is the expected value of variance of x and y when they are independent? Its expected value of x and y x times y minus expected value of x and expected value of y. But what is the expected value of x times y? Given that the joint distribution is equal to the product of the distribution, let me even put that formula here. Assuming that these things could be that'll be f of x, y of y times x times y dx dy, right? This is how you write it. Okay. Expected value of x and expected value of y. Do we agree with this? Because this is the joint distribution, right? When they are independent, the joint distribution is the product of the distributions. That's the definition of it. Now, because this thing is a product, it's same as integral from negative infinity to infinity, x, f of x, dx, times integral from negative infinity to infinity, y of x, y of y, dy. This can come out of the integral. This constant can come out of this integral, and you're left with that. Right? Expected value of x, expected value of y. And this is nothing but expected value of x. And that is nothing but expected value of y. And expected value of x, expected value of y. And that's 0. So When the random variables are independent, the covariance for independent variables x and y, covariance of x, y equals 0. And if that is the case, then the correlation is also 0 because the correlation is equal to the covariance divided by this product of the standard deviations. And the top being 0, the whole thing is going to be 0. This is why the correlation is 0. Questions? Now let me compute in one example here, okay? A second example, let's say we have the joint distribution equals x plus y, 0 is less than x less than 1, 0 is less than y less than 1, 0 otherwise. And so I'm going to look at the covariance. What is covariance of, question is, what is covariance of x, y? What is okay. How do we find this? First of all, start by finding expected value of x. How do we find expected value of x? By integrating over the whole range x times the joint density, right? And the range is this. It's a rectangle, beautiful range, so we don't need to worry about a graph. 0 to 1, 0 to 1, x, because that's what you're taking the expected value of.
Dr. Longlow, that's the screen.
Times the density. Thank you. And the density is x plus y. So times x plus y. dx dy. Do we agree? All right. So we compute this integral with respect to x. That's integral 0 to 1. We integrate x times x, that's x squared, gives you x cubed over 3, plus x squared y over 3. 0 to 1 dy. So plug in the numbers, 1/3 is x squared over 2. So it's 1/3 plus y over 2 equals 0 to 1 dy, which is 1/3 y, is y squared over 4. 0 to 1, that gives 1/3 plus 1/4, that is 7/12. So the expected value of x is 7/12. Now, please, if we can save some time, tell me, do you see that this distribution is symmetric? And the range is symmetric as well. X is from 0 to 1, y is from 0 to 1, right? And if you switch x and y in the formula, it changes nothing, right? That means expected value of x equals expected value of y. But it doesn't matter which of them you're using to integrate factors. So due to symmetry, I'm in French words already. So expected value of x equals expected value of y equals 7/12. Now we need to find the variance. So sigma squared x For that same reason, sigma squared x is also equal to sigma squared y, right? Due to that symmetry of the joint distribution. They have the same values. So it's equal to expected. Thank you for reminding me that I don't see that. I keep forgetting to look at that board. So it's going to be expected value of x squared minus 712 squared. And so expected value of x squared is, again, we're taking that same integral, replacing x by x squared. So that's integral of 0 to 1, integral of 0 to 1, x squared times x plus y, dx dy. Minus 7 squared. So how do we compute this? You do integral of 0 to 1, and inside there you integrate x cubed, and that's x to the 4th over 4, x squared y, and that's x cubed y over 3. Then plugging 0 and 1, then dy. If you do this and you do the other one, you obtain one fourth. That's 1. Please actually agree with me. dy minus 712. And this is going to be integral of 1/4 can be y over 4, so that's 1/4. Plus integral of y over 2 is going to be 1/6. Minus 712 squared. This whole thing, somebody tells me, is equal to 11 over 144. So that's sigma squared. Then you want to find the expected value of xy. To get the correlation, you need one last thing, the expected value of xy. Which is integral over that same range, 0 to 1, 0 to 1, of xy times x plus 1. Yes, dy. Okay, so this can just tell you what the answer is. Xy expected value of xy minus 712, 712 for expected value of x, 712 for expected value of y. And this gives you negative 1 over 144 after computing that here. And so you can have that rule of xy equals covariance of xy divided by sigma x, sigma y, which is in this case negative 1 over 144 square root of, what's the number we got there for that? 11 over 144 times square root of 11 over 144, because they are same. So that's negative 111. So the correlation of these two random variables is not that big, but it's not 0. It's negative 111. two random variables have an inverse correlation. That's it. Sorry for eating into your time. If you have any questions, feel free to ask them. Otherwise, see you next time. 11. Yes. So this is square root of 11 over 144, square root of 11 over 144.